This is the third of 3 videos in which I'm exploring the phase structure of 3 imaginary mineral substances, anarite, elendite, and isildite. I've made up these substances, but they're all meant to represent different crystal structures with the same underlying chemical composition. These are different crystal structures that are favored under different environmental conditions of temperature and pressure. In previous videos, in our first video, we worked out at constant pressure, atmospheric pressure, we worked out what temperatures each one of the 3 phases was the preferred phase. We found that at room temperature, isildite has the lowest Gibbs free energy, and so it is the stable, the preferred phase at room temperature, and that was true between 237 and 893 Kelvin. But below 237 Kelvin, we found that anarite was the preferred phase, had the lowest Gibbs free energy, and above 893, elendite had the lowest Gibbs free energy. Now, that was all done using an approximation where we approximated the difference, we took the approximation that the difference in entropy between 2 phases was constant as we changed the phase, as we changed the temperature. That wasn't bad over the small difference here. It was pretty cruddy over the large difference over here. In the second video, we found that instead of 893 Kelvin, we were able to make a better estimate that got us to, what was it? It got us to 730 something Kelvin, I think, as a better estimate we made by you taking an average entropy over that range, the average of the entropy over the range, and I commented that a full numerical calculation would give you a 714 Kelvin thing. For today, for this final video, we're going to use our original values because we want to tell a self-consistent story, and our way of estimating the phase diagram at different pressures is not going to take into account the way that the entropy, these corrections to the entropy. It's going to assume that the difference in entropies is constant. So because we're going to make that assumption, I want it to be a self-consistent story. We're going to use our original 893 and 237 instead of the better 714 and 238 numbers that go in here. Okay, what do we want to do? The Clausius-Clapeyron relation is our goal. I should probably have put a diagram space over there, but we'll work with this. What I want to do is understand not just this temperature axis, but a pressure axis as well, and to say if I know that these two phases, anarite and isildite, these 2 crystal structures, have equal Gibbs free energy here, what happens when the pressure gets higher? As the pressure goes up, does it stay the same temperature? Does the temperature of the equality shift from one side to the other? It's an interesting question. Here's what we've got to do. We're going to say, we're going to look at that, and we're going to look at the thermodynamic identity for G. And we're going to say, along a phase boundary, along the, let's be specific, the anarite-isildite phase boundary, along that phase boundary, wherever that goes in temperature and pressure land, along that phase boundary, we know that the Gibbs free energy of anarite as a function of temperature and pressure will equal the Gibbs free energy of isildite as a function of temperature and pressure. It has to. That's what it does. That's how that works. And so, in particular, since those are equal, if I move along the boundary, if I make a tiny change, if I make tiny changes in temperature and pressure that follow the boundary, that means that the change along the boundary of the Gibbs free energy in anarite has to equal the change of the Gibbs free energy of isildite. So it has to be true that dGA has to equal dGI to keep this true. To maintain this along the way. To keep it true, that has to be equal, or else if one of them were changing faster than the other with the same change of temperature and pressure, you wouldn't be on the boundary anymore. But I can use my thermodynamic identity and set this up and say that minus SA dt plus VA dP has to equal minus SI dt plus VI dP. And hey, this means I can now lump these things together. I can group together the dP terms, group together the dt terms, I'll find, subtracting this from both sides, I'll find that volume of anarite minus volume of isildite times dP equals, adding this to both sides, entropy of anarite minus entropy of isildite dt. Or in other words, if I want to know the slope of a phase boundary in pressure versus temperature space, I can find that dP dt, the slope of the phase boundary, is just equal to, divide by dt, I'll get S anarite minus S isildite divided by, divide over there, V anarite minus V isildite. Or in other words, delta, in our notation, delta AI of S divided by delta AI of V. This is called the Clausius-Clapeyron relation. Well, one version of it anyway. There's also a version in terms of the latent heat. But this is Clausius-Clapeyron as we're going to use it here since we don't have latent heat data. We've got this story. This is the Clausius-Clapeyron relation, and we can use this. We know those things. Again, this is true even if these are not constant. If the entropy is changing as you move along your diagram, then of course this slope will not be a straight line. We're going to make the approximation that the slopes are straight lines. We're going to approximate as constant this whole deal. We're going to treat this as a constant, and so let's see where that takes us. We're going to say, for example, that for the AI boundary, we're going to say that dP dt, I'll label it as an AI. We're going to say dP dt for AI is equal to, well, that difference in entropies between the two, AI, this minus this, I've seen that before, that's 4.9, negative 4.9, negative 4.9 joules per Kelvin, divided by my difference in volume between the two, delta VAI, A minus I. This minus this looks like that is minus 3. I should double check my numbers just to make sure I have that right. That difference in volumes is minus 2.9 cubic centimeters. And these units are weird, right? These aren't useful units. I'd really like my units to be something like pascals per Kelvin or bar per Kelvin, something like that. Joules per Kelvin. Well, so here's what I'm going to do. I'm going to multiply by 100 centimeters over 1 meter quantity cubed, and that will cancel out my things there. So this is going to end up being, if I work out my numbers, 1.69 times 10 to the 6th, and this is joules per meter cubed Kelvin. And a pascal, 1 pascal of pressure is 1 joule per meter cubed, it turns out. So this is pascals per Kelvin. I have a slope. That's great. Now the units that I'm usually going to use, the units I want to use for pressure are bars, because 1 bar is about 1 atmosphere, it's 10 to the 5th Pascal. 1 kilobar is 1,000 bars, it's 10 to the 8th Pascal. I want to use kilobars as my vertical units because we'll find that's the scale over which these things change. Kilobars are relevant for geology. If you go, a few kilometers into the crust, you get into kilobars of pressure. So we're going to multiply this by 1 kilobar over 10 to the 8th pascals, and we're going to find that this ends up being it's 0.0169 kilobars per Kelvin. Or this is a little weird to write down. I guess I could have written this as 16.9 bar per Kelvin. Units that I actually quite like, because the range of Kelvin we're looking at is hundreds here. Sometimes for drawing a graph, it can be useful to write this as 1.69 kilobar per 100 Kelvin. So for each 100 Kelvin that I move across my graph, which is a sort of convenient size for typical things, for each 100 Kelvin there, I'll go up by 1.69 kilobar. That's what this result's telling me. All right, so I've got a slope, and that's kind of cool. I can I'll draw my phase diagram up here. This will be a good place. Drawing my phase diagram up here. Let me sketch this out. I've got vertical and horizontal. And my horizontal scale here, this is temperature in Kelvin. And this is going to be pressure in kilobar. And I think the scale I wanted to go with was going about 2, 4, 6, 8, 10. And temperature, I need to get all the way over to about 1,000 Kelvin over here. Well, let's call this, 1,000 Kelvin. So I need 2, 4, 6, 8. I think I did that pretty well. 200, 400, 600, and 800 Kelvin. What I have here, I have a slope of the AI phase boundary, and I have one point on it, and a point and a slope determine a line. The AI phase boundary starts at 237 Kelvin, so that would be, I guess, 298. Our room temperature, just for reference, is about 300. So room temperature is about there. That's T naught, our room temperature. So 237 Kelvin is going to be about, that'd be 250 here. That's that. And I got 1.7 kilobar per 100 Kelvin. So if I were to go, say, if I were going to go over by 400 Kelvin, 400 times, so 400 Kelvin would be 4 times this. 1.69 times 4, that'll get me up to 6.8 kilobar. So 400 Kelvin, 6.8 kilobar is going to be almost 7, going to be here-ish. So it looks like I'm going to have a line. Oh, I missed a little. Here, it's not even that accurate. Got a line that goes something like this. So that's a line where I have anorite is the preferred phase over here, and iseldite is the preferred phase over here. I've constructed a phase boundary. That's how this Clausius-Clapeyron business works. I've just used that to construct a phase boundary, and I can do the same thing for my elendite-iseldite phase boundary. The exact same story. I can say that dp dt for my iseldite-elendite boundary is going to be my delta S, difference in entropies for the two. Let me just pull this up here. Minus 3.7 joules per Kelvin divided by my volume difference, this minus this, is going to be positive 3.4 cubic centimeters. And you'll notice this is negative. The number I wind up getting here, when I put that together, is 1.09 times 10 to the 6th pascals per Kelvin. That's what I have here. Or if I wanted to put it another way, I could say that would be, that's 10.9 bar per Kelvin, or it is 1.09 kilobar per 100 Kelvin. And so, but these are negative. I forgot my minus signs. Minus, minus, minus. So that's going to be at 1.1 kilobar per 100 Kelvin. That is the slope of my line, and I'm doing point slope, right? So that's my slope. And I have a point. Remember, I'm using the 893 because that was the consistent, so linear approximation. 893, so that's about 900. That's going to be about here. and I've got a slope of minus 1 kilobar per 100 Kelvin. So every 100 Kelvin I go down, I go up by 1 kilobar. So let's see, that'll by 1.1. So that's 1.1, 2.2, 3.3, 4.4, 5.5, 6.6, 7.7, 8.8, oh, that's 9. 9.9, there we go, 9.9, that's right up here. So I could just connect those dots. That is my boundary between elendite on this side and iseldite on this side. That's a boundary. Now, this big X is making me feel a little uncomfortable, right? Because I've contained this, but A or E, which one? Obviously, it's not consistent up here. I haven't ever said anything about the boundary between anorite and elendite. These two, iseldite is contained down here. I can already sort of see where the iseldite region is going to be. It seems to be sort of, this is my iseldite region. That's where that substance, that version, that is the preferred form. But what about anorite and elendite? I know that iseldite is preferred over elendite down here, but not there. And yeah, so what's going on up here? I need one more calculation, don't I? I need that last calculation. I need to find my dp dt for, well, two more, but yeah. I need to find that dp dt for anorite and elendite. And there I can do the same calculation. I wrote this down earlier. I've got this somewhere. Minus 8.6 joules per Kelvin. Is there a difference in entropy? Joules per Kelvin. Is there a difference in entropy? And minus 0.5 centimeters cubed. Is there difference in volume? They have very similar volumes. The anorite and elendite volumes are very close together. So that's a positive slope. Is it really a positive slope? That shouldn't have been a positive slope. Let me double check. Difference in entropy, AE. Anorite minus elendite here is a negative number, and this one is, oh, that's a positive 0.5. Positive 0.5, I feel better now. That my stat is positive 0.5. Good. It's a negative slope, but that number divided by 0.5, that's big. 16, what's that, 17.4? Negative 17.4? I'll just call it negative 17. Negative 17 times 10 to the 6th pascals per Kelvin, or in other words, negative 17. That's big. It's going to be negative 170 bar per Kelvin, or in other words, in other words, negative 17. That's a 17. Negative 17 kilobar per 100 Kelvin. And I've got a slope for that. I don't have a point. But we need a point and a slope to draw a line. I've got a slope, I don't have a point. Now, there are two things I can do to find that point. One of them is to say, where these two lines cross, where those two lines cross is a point where G anorite equals G iseldite, and also a point where G iseldite equals G elendite. So all three are equal where they cross. So that is a point on this line. The other thing I could do, if I want to be vaguely, if I want to do a double check along the way, is that I can find the point, using our earlier methods, I can find the point where the GA and GE are equal at standard temperature, even though they are neither one's the preferred phase there. I can remember how we find that point. So if I know that G anorite of TAE equals G elendite of TAE, if I know that's true, then I know that my difference in G's is 0, and so I have 0 equals delta AE of G, temperature TAE, and using results from before, we had worked this out. This was equal to the difference between anorite and elendite of G at T naught, and again, a linear approximation, or a simple thing, minus the difference in entropy between the two phases, A and E, times TAE minus T naught. So I can work out then that TAE at standard pressure is T naught plus delta AE AE of G of T naught over delta AE of S at that T naught. And for us, I'll come down here. This equals 298 Kelvin plus my difference in Gibbs free energies was AE. I should have this in my notes just so I don't have to do it in front of you. I get minus 1.9 kilojoules, minus 1.9 kilojoules difference in Gibbs free energy for the two of them, divided by my difference in entropies, which was minus 8.6 joules per Kelvin. I get from that 298 Kelvin plus, this will be plus, and when I work it out, I get 221 Kelvin, or in other words, adding it up looks like, adding it up comes up to 519 Kelvin. And again, that's not going to be exactly right. If I did a more careful treatment or if I did an average, I'd do it. But for this consistent story, I want to use this. 519 Kelvin, 500 would be here. 500 would be here. 550, 500, here-ish. I'm being way too precise for a thing like this. And minus 17 kilobar per 100 Kelvin. So that means if I go 50 Kelvin, so 50 Kelvin's pretty small, I'm going to go up by half of that by 8.5. 50 Kelvin is only about that far, and 8.5 is about here. So it's going to look something like that. Something like that. And remember, that's a line where on one side, Anarite is the preferred phase, and on the other side, where did I put it? On the other side, Ellendite is the preferred phase. And so I've got that line. What I have to do here is, you'll notice I've got too many lines now. I've got this line here that tells me whether A or E is preferred, but it doesn't matter because I is preferred in that whole region anyway. I've got this line that tells me whether I or E is preferred, but it doesn't matter because A is preferred in that whole region. So I can get rid of this part. And similarly, this line tells me whether A or I is preferred, but E is preferred over there. This is my graph. This is what I can do. And A, I guess, is the preferred form all throughout here. And E is going to be the preferred form all throughout here. And I've constructed not a bad phase diagram for Anarite, Ellendite, and Isseldite by putting this together, by putting these pieces together. So let me remind you of what went into this, now that we've done the whole story. First of all, this diagram with its straight lines is constructed very much from the linear approximation saying the delta S's are constant, the differences in entropy are constant. And so what we did to do this, we found 3 points on this line. I guess I could have labeled that one down here too. My AE point at 519 Kelvin, somewhere somewhere pretty much in the middle of this whole thing. There's my 519 Kelvin AE point. What we did, we used our Gibbs free energy equality to find the 3 points at reference pressure, 3 points where we had a specific where we had a specific pressure where the two Gibbs free energies were equal. A equals I, A equals E, I equals E. We found those 3 points. Then we used the Clausius-Clapeyron relation over here to find the 3 slopes. The slope of each boundary, putting those pieces together. And Clausius-Clapeyron gave us 3 slopes. And when you have a point in the slope for each boundary, you can draw the lines. It is no coincidence that the 3 lines met at a single point in the middle. They had to. Like I said, each line, this is GA equals GI, this is GI equals GE. So clearly the GA equals GE line must also go through that same point. The slopes and points are not all independent. They're related by those equalities, by the definitions of those lines. So they all had to meet at this point. That's, by the way, why I didn't just shift this line over the starting point, because then that would have shifted over, but I wasn't changing the slope. So yeah, this is better. So I've got this story. I think it's actually a pretty good story. I think it does a solid job of figuring out what this looks like, and we were able to get a good visualization of where each of these is stable. If you were a geologist studying these imaginary minerals and you found an outcrop of elendite crystal structure in some rocky outcropping somewhere, you would know that elendite must have formed at both higher temperatures and probably higher pressures somewhere in this region when the rock that made up that outcropping was first formed. You would have known that those are the conditions where that showed up. If the outcropping had been anorite instead, you would have known that it was a much lower temperature situation. And if you had an outcropping of isildite, there would have been a cap on how much pressure there could have been, so that isildite must have formed closer to the surface of the Earth and not as deep underground where the pressures are higher. There's a lot you can deduce from a phase diagram like this, and obviously the true phase diagram, if I were going to do the real version, the true phase diagram has a little bit more bending of this, and this line comes down earlier, and there's a little bit of a bend over here or something. There's some bending and things, but overall, this does actually a pretty darn good job of modeling. Our straight line things does a pretty darn good job of modeling what this system behaves like and how it works. And so I really enjoy constructing these phase diagrams. I hope that you can focus on, I know I've done derivations along the way here too, but I hope you can focus on just using some of these tools, using the equality of the Gibbs free energies and this linear approximation, using the Clausius-Clapeyron relation and finding those slopes, and then drawing the diagram. I hope that's something that makes sense to you, and I hope that this example is something that has helped you see how it plays out in a realistic looking scenario.